So I'll be talking about this. Okay, so I'll be talking a little bit more about the computer science side of machine learning, and in particular some engineering applications. And I focus on networks and graphs. I'll use those two words interchangeably, and I'll be showing some interesting applications in a social science setting where we're starting to look at networks of places and people from location data, which is work in collaboration with my startup as well called Sense Networks. So we all know that, going back 20 years, we all know that graphs and networks are important, and there are these giant networks like the World Wide Web, and the key property to exploit in these types of networks, unlike other, let's say, standard data, isn't quite so much the attributes of all the different points or the nodes, but really the link structure. And so companies like Google have changed the way we look at the collection of websites out there from whatever it used to be, just a collection of documents, to really this network where the links are really important in identifying similarities between websites and basically how they link to each other. And so we've got this network of online places called the World Wide Web, and there's all sorts of lucrative opportunities if you model this network. There's also the network of online people, which is social networks online, such as Facebook and so on. And again, some of the key properties are the links between people. And so if you are friends with someone, then that means you're very similar. You don't necessarily have to have the same attributes, but there's a lot of affinity based off of this link structure. And again, companies like Facebook and other companies are using this type of structure to send you, let's say, promotions and ads and collaborative filtering and recommendations based on these types of network structures. So networks are very important. And what I'll be talking about is what's next, which I think is going to be an interesting new type of network, which is not just a network from, let's say, online places or network of online people, but a network of real places and real people. And how are we going to do this? Well, online data is easy to get. How do we really model the network we have of real network places, really real places out there in the real city, the real network of places, and the real network of real people? And so I'll be talking towards the end of the talk about how you can build these types of networks from location data. So each one of us has a cell phone right now. We're all collecting data about where we are located. It should be pretty easy to figure out that we're all co-locating at this conference, and so there should be some kind of social network that's been built automatically, all of us having to link on Facebook and saying we all are interested in similar types of things. So I'll talk about that later, but first I'll talk about some of the algorithms. So this is what the company is doing, is it's basically enabling this recovery of a network from location data. Once you have that network, then you can do all these interesting online types of things that people are doing, let's say at Amazon and Yahoo and Facebook. Basically, collaborative filtering, marketing, advertising, smart search, social recommendation, and so on. So we'll get back to this, but first I'll talk about the technologies that we're using. And throughout this talk, I'll be using the words graph and network interchangeably. And the key thing is to go from data to a graph. And so once you've converted your data set into a graph, there's many algorithms. A lot of them come from graph theory and computer science and combinatorics that you can apply to these graphs that give some really nice either embeddings of the graphs, which are low-dimensional visualizations and reconstructions of the graphs. You can do things like partition the graph into two pieces, which is related to clustering. You can do things like label the graph, which is related to classification. A lot of the machine learning types of problems have analogs in the graph theory world. And after we've looked at some of these tools, I'll go back and talk about the graphs you can build from location data. So how do we go from data to a graph? There's many ways to do this. I'll just go through some of the simplest ones. I'm given some sample data. So these are 6 samples, x1 to x6. These could be pictures of cats or any type of observation. And one thing you could do is build a graph between these types of objects. And you can build a graph pretty easily by just defining a similarity function. The similarity function says for any pair of objects I can compute how similar they are, or some kind of kernel between the pairs of objects. So this is the kernels that Tom was talking about, for instance, you could use right here. And then this graph is just a matrix, which is all the pairwise kernel evaluation between all the objects. Another thing you can do is convert kernels into distances, if you prefer that kind of analogy, and you can always use a simple square root trick to get distances out of kernels. There's many possible kernels. I won't go through all of them. Gaussian kernels, Laplace kernels, polynomial kernels, all sorts of probabilistic kernels that come from the statistics community that let you build this graph. But at the end, what you have is basically this fully connected network where all the pairs of nodes have a strength between them, just a single number that's saying how similar these two objects are. And so one of the things we're going to be doing with a lot of the graphs is actually just taking a look at them and visualizing them in 2D. These might be really large, ugly networks. We'd like to picture them in 2D before we start doing other operations on them, like classification or clustering. So converting this graph into visualization is also called graph embedding. There's a classical approach to doing this once I have this matrix and all these edge weights, which is called spectral graph embedding. And it goes back to Fiedler and Hall in the 70s and even earlier. And the basic idea is to use the leading eigenvectors of that matrix A and just to draw the coordinates of the graph using the values of the leading eigenvectors, or the Laplacian of A. And so it turns out if I use this kernel and I have this type of graph over here, I get this nice one-dimensional visualization of the data. And I've actually reduced the dimensionality of the graph, and I can picture it very nicely as just a linear graph, really, or a line here. And so it turns out this type of graph embedding is actually equivalent to kernel PCA, which is a very popular method for dimensionality reduction for data. And that goes back to Sholkopf and so forth. And unfortunately, if you use the wrong kernel, then this technique does not work very well. Because if I use just a simple similarity function between pairs of points, which is just their inner product, then I get back a 2D visualization of my 2D data. So I haven't really understood or summarized the data in any way. And so the key isn't really so much, so you really need to know the kernel, but the other real problem is what you're doing when you're running these graph embedding algorithms is you're preserving all the distances in the graph. And it turns out if you want to preserve all the distances, when you use the wrong distance metric, you're going to have very little dimensionality reduction. So instead of doing that, one idea is to work with sparse graphs and say only preserve a few of the links in the graph. And then you can get something like the upstairs visualization. And so some of these ideas have been around for a while. Some recent very competitive methods are based on sparse Laplacian embedding or semi-definite embedding by Weinberger and Saul. And actually these things work remarkably well. But you need to get a sparse graph. So we had that fully connected graph. How do we get a sparse version of it? Turns out if you really want to enumerate all possible subgraphs from that fully connected graph, that's a really big space of 2 to the n squared, roughly, possibilities. So you want to find a quick solution. One of them is just to threshold similarities and say I'm going to cut off if your similarity is below something. That gives you this type of picture. That's not always good because you can get really disconnected bits and pieces in the graph. Another idea is you can find the best tree connectivity for the points and say I don't want to use full connectivity, just connect things up with a tree. But the most popular thing is just to keep around the k nearest neighbors. So that's kind of the intuitive thing that I'm going to find who are my most similar, let's say, nearby exemplars and connect to them. And so in order n squared time, basically the amount of time it took to calculate all these distances, you can say, well, let's let each point keep around its 2 closest points, the ones with the highest kernel value or least distance. And so we go from that matrix we had over here, which was to a simple connectivity matrix, which puts zeros and ones, saying, am I linked to this person, yes or no? So from this matrix, we can get this matrix just by running k nearest neighbors. It's a very simple algorithm. And so then, now we have a sparse graph, and this is what the semi-definite embedding algorithm does. So this actually works very well. You improve the spectral embedding technique by solving what's called a semi-definite program, which is something you can do very efficiently. It takes cubic time. And it basically unfolds the sparse graph. So you take your graph and you imagine metal links. So here's the original data. We formed a k nearest neighbor graph across all the points. Then imagine taking this graph and stretching it in all the directions. Just grab it and pull it in all the directions. And that what ends up doing is it'll snap the graph tight, and you'll get something that looks flat. And now if you look at this flat version of this snapped kind of flat graph, it's very easy to compute the top eigenvectors there and recover a 2D visualization from this 3D data. Okay, so how do we do kind of this unfolding and snap the graph by pulling? Well, you saw this thing called a semi-definite program. It says you gave me the A matrix here, which was the matrix of distances. C told you who was connected to whom. Find another matrix, K, which is really big. Maximize the trace of K. So it stretches in all the dimensions, subject to some simple conditions on K, that it's a real embedding, for example. And then make sure all the distances in K agree with the original distances in A. So if there was a link here in the original A matrix, the K matrix should have that same distance. So that's like putting a bunch of metal rods between the points. Everything else can move, but the points connected by metal rods can't move away or closer to each other. They're really rigid rods. And that gives you something like this, which works pretty well once you take the eigenvectors of it instead of the original.
So the reason why it's called semi-definite is because the solution for this optimization is semi-definite.
Yeah, exactly. So it's because you're solving a semi-definite program. It's also called maximum variance unfolding, because you're just unfolding the graph by pulling in all the directions. So this is roughly what's going on. You're pulling in all the directions, and you end up taking this Swiss roll, and you make this nice flat version of it as you run this algorithm. Okay, so this works great. Are we done? Is this the best thing that can be done to the data set? So it turns out this is a good intuition, but it doesn't always work. And for example, here's a simple graph called a star graph. So all the points are connected to this point in the middle, something like a prototype with all the things hanging off of it. If I take that graph and I pull it in all the directions, I end up not flattening it out, but I puff it out into a sea urchin or some kind of puffy thing in 7 dimensions when I pull in all directions. And I go from something that's roughly 2-dimensional to something that's actually 7 or 8-dimensional here by pulling it in all the directions. And so here's the original data set. If you just do PCA or spectral embedding, you can get something that's almost 2-dimensional, and it looks pretty good. But if you run this algorithm, it actually goes in the opposite direction and doesn't reduce dimensionality, it increases dimensionality, because pulling in all directions doesn't always increase. So it doesn't always decrease. So we have another algorithm that we suggested in 2007, because this idea of pulling in all directions doesn't always work. It fans out some manifold and some graphs. Instead, we do this thing called minimum volume embedding, which says unfold in only the 2 principal directions you're going to keep and squash down on all the others. So pull in these 2 directions and squash down on all the others. The big directions should get as big as possible. The other directions should get small. And you can imagine if you had a map you were looking at, you would unfold the map, and then you just run your hand over the map on top of the table to flatten it out a little bit. That's the idea behind the algorithm. And it's very simple. In fact, the algorithm is almost like the old algorithm, just iterated a couple of times. Let's say I want to keep around only 2 dimensions. I want the eigenvalues in those 2 dimensions to be very large for that graph, and all the other eigenvalues to be really small. So these 2 eigenvalues should account for kind of 100% of the energy of the graph. Like this, the composition of that matrix K, it should be pretty much close to 100%. So that means that we call this score the fidelity. So fidelity of 100% means the graph is completely described by just those 2 dimensions. So you want to maximize fidelity, and it turns out here we had a pretty good fidelity of 0.98 to start off with before we ran the algorithm, and now the algorithm went and reduced fidelity for us. That's bad. So instead, we want to just maximize this quantity called the fidelity. And instead of maximizing this ratio, you can say, well, maximize this guy minus some scalar of the times the denominator. That's totally equivalent to maximizing the ratio. And so for a particular choice of beta, you can maximize this by maximizing this. And we pick beta equals 1/2, but again, there's ways to figure out what beta should be. And so the algorithm is basically the same as the previous algorithm. You just have to iterate the semi-definite programming a couple of times, but then you go from this toy example really to a 2-dimensional visualization here. I've pulled in 2D, the 2 big dimensions, the squash down on all the others. And it converges basically by running this algorithm 5 times, just 5 or 6 iterations. And here are some simple social networks we ran it on. And you can look at the eigenvalues, and it needs far fewer eigenvalues to reconstruct the social network than SDE or spectral embedding. These are just social networks where people declared friendships. Here are some tree networks of phylogenetic trees. If you took a tree network, these are salamander species and how they evolve from each other. If you just do a spectral embedding of that network, it doesn't really look like a tree. Neither does the SDE method, but we start recovering things that look like trees and actually capture most of the fidelity in 2 dimensions. Yeah.
So do you use these embeddings mostly for visualization purposes, or is it also, does it have a modeling purpose?
So we use them for visualization, but we also have done things like use these to cluster. So once we visualize, then we run clustering algorithms and things like this.
How does it get to, I thought your earlier topic is how to form a graph from the data.
Yeah.
How is that related to that?
So far, we're given a graph, which is the case for these salamanders and the social network, or we do a k-nearest neighbor graph. So actually, that's the next slide.
Oh.
So here's a k-nearest neighbor graph that someone's built from face images. And so you take a bunch of face images, compute the k-nearest neighbor graph, and then run spectral embedding on either the full graph over here, or you do this unfolding on the sparse graph, or use our minimum volume embedding. The important thing is we just get the full graph represented in just 2D here. So 99% of the eigenvalue energy is in here, is in 2 dimensions. You need 4 for SDE, and you need many more for the PCA technique, or the spectral technique.
Minimum spanning tree.
Yes. So right now we're just using the k-nearest neighbor graph here. So you could try the spanning tree methods, but for these types of images, you don't really want a tree structure on what's going with this data set. So again, you can continue to look at other data sets. The key is you can pretty much represent this network between the data or the images, this k-nearest neighbor graph, in 2 dimensions instead of needing many dimensions. And so this is a nice way of capturing all the pairwise distances in your data set in just 2D. Not all, sorry, the ones along the k-nearest neighbor graph, that sparse version. And so here's some fidelity scores. Again, we get really high fidelity. It's not too surprising because we're maximizing the fidelity with our algorithm. So, but again, you're really seeing this network that's got a lot more dimensions by first sparsifying it and then trying to preserve all the distances in 2D. So this works well. But I'll talk about a problem in just a second, which is a problem not with this algorithm so much, but a problem with k-nearest neighbors. And so actually this is the subject of a lot of my research. I'm very interested in matching and matchings and generalizations of matchings, and I'll talk about that in a second. So why is k-nearest neighbors bad? So it turns out k-nearest neighbors, or just taking your data and finding closest points and saying that's how I'm going to build a graph, can go terribly wrong. So here's an example where I've got 2 rings. There's two classes of points. There's points on the inner ring, points on the outer ring. If I said, well, now connect every point to its 2 closest neighbors, you'll get this type of connectivity, the inner ring and the outer ring. Things are nice. And that's because there's about a dozen samples on each ring. There's a dozen points on the little ring and a dozen points on the outer ring. And also the little ring is much smaller than the outer ring. If the little ring starts to grow, then I start getting these across ring connectivities. Okay, if I just have everybody greedily grab their 2 closest neighbors. Another even more dramatic problem is if the number of samples on each ring starts to shrink, then the outer ring points start to pick the inner ring points because their neighbors are too far away. And so this happens in 2D in this example, and you get this strange behavior where these outer ring points are starting to pick the closer ones, but it happens more quickly in higher dimension. In fact, the problem is related to this quantity called the kissing number, which grows exponentially with dimension. And things like this happen really quickly in high dimensions. It's harder to show this in the 2D case because it looks more contrived, but in high dimensions, this is always happening. So, and imagine, so it's because each point, when they're grabbing their 2 nearest neighbors, they're running this simple rule, which is, who are my 2 neighbors? I'll connect to them. And then we all run this algorithm, and at the end, I might have actually been picked by many more than 2 people. So if everyone in this room said, pick your 2 closest 2 neighbors, the people in the middle would actually get picked very often because other people would pick them, whereas the people on the outside of the room only would have 2 neighbors because no one would pick them back. And that's what's happening here. Okay, so how do we fix this problem? And there's a very nice solution to this problem called a K-matching. So if we run K-matching on these rings, we get back exactly the right connectivity. And so the K-matching algorithm is saying, don't just run this greedy procedure of grabbing your 2 closest exemplars. Instead, let's run this algorithm which minimizes the amount of string we need to connect to each other, and each one of us can only hold 2 pieces of string, basically. And that's the K-matching algorithm. So it's a little more complicated than k-nearest neighbors, but it's not hard to implement, and in fact, Google uses this to do that online advertising. This is what's running behind the scenes in Google AdWords. They're solving generalized matchings. Okay, so what Google's trying to do, and here's the simplest version of it, is match advertisers to search words to maximize profit. And so matchings are sometimes called permutations, assignments, the symmetric group. They're basically a sparse graph, and there's an n factorial number of matchings. But you can find the maximum weight one in cubic time with this Hungarian marriage algorithm. And that takes n cubed, and it's basically maximizing the dollars. So if I said, here are 3 advertisers and 3 words, connect 1 to 1, 1 advertiser to 1 search word, and maximize the dollars in this matrix, this is the solution you get. You connect Apple to laptop, and IBM to server, and Motorola to phone, for example. And that maximizes dollars. So if I was trying to send an ad, and IBM said, well, I'll give you $2 if you show my ad when somebody types laptop, or I'll give you $3 if you show my ad when someone types server, this is the best way to set up the advertising, because you have to have a one-to-one relationship here. And so this is the maximization problem. You're maximizing the dollars subject to C summing to 1 this way and summing to 1 this way. So that's called one matching, or the simple type of matching. So what's K matching? K matching is really just a natural generalization, which is C has to sum to a number K across the rows and across the columns. And so you just replace those constraints with K instead of 1. And this is more general than one matching. It's called K matching, and it produces K regular graphs, or K marriages. And you can solve it, again, in cubic time with this technique called Edmonds blossom. So we've been using this algorithm, which goes back to the 60s. It's actually a beautiful algorithm. The paper and this blossom technique is really kind of wonderful combinatorics and graph work. And so here's what Google's really solving, of course. They show 3 ads in their sidebar. They don't show 1 or 2. And each advertiser also gives a quota, which is Motorola says I can only do 20 ads a day. Apple will say I can do 500 ads a day. So there's quotas this way and quotas this way. And then they say maximize dollars subject to those quotas on the rows and the columns. And so you can actually handle all these cases. This is called generalized matchings, where the sums in the rows and the columns are just arbitrary numbers, different Ks. And so that's what they basically solve. It sums to 3 across the rows. They don't actually use Edmonds' algorithm because it's horribly slow. They use Vazirani's algorithm, which is approximate and online, and gives you about 63% of the maximum profit you could achieve. That 63% is still $21 billion a year, so it's not so bad. But if they were able to run an exact algorithm offline, they would get even more money.
But this one should be done dynamically, right? Because every now and then, you running out of advertised money, then
Yeah.
the cost like everything. Well, the cost is fixed, but once you run enough of those, gets rid of it. So it should be dynamic. According
Yeah.
to this, it's a static. It doesn't change.
Well, this Vazirani algorithm is online. It's dynamic.
Oh, so it runs every now and then.
It always updates based on what just happened. But you can imagine running a mini batch version of the online with a better algorithm. So again, I don't want to spend too much time on this. You basically have to find the maximum weight K matching, and K nearest neighbors just tries to make everybody sum to 3 this way. But then if you look at what happened, this guy got picked by 5 people. He no longer sums to 3. And so K matching enforces the sum to 3 this way and sum to 3 this way constraint. Okay, and so it turns out Edmonds is slow, too slow for any fun applications. Vazirani's is approximate. Can we do better? And in 2007, Bert Huang and I proposed solving this problem with belief propagation, which is a very popular tool in graphical models and in statistical inference. The basic idea is to set this up as a probability distribution on all possible solutions, all possible K matchings. And we're going to try to find the maximum likelihood solution, the sigma star matching. And so we set up this graphical model. Upstairs you've got the advertisers, downstairs are the search words. And each one of these has a variable which is who do I want to marry or pick, and each one of these are who do I want to marry back. So which advertisers does the search word want to connect to, and which word does the advertiser want to connect to. So these are the random variables. And it turns out this distribution factorizes into a product of everybody's let's say, dollar incentives to connect across to the other person, and then these functions which enforce reciprocity. So if I connect to you, you have to connect back to me. If not, the whole score goes to 0. It's not a valid matching. So you can run this, you can find the maximum likelihood solution by running an algorithm which just sends messages on this graph called belief propagation. It's the simplest possible algorithm. And what's remarkable is, so you run this algorithm on this graph. If the graph is a tree, it's known that we'll get the optimal answer. And that goes back to Judah Pearl's result. If it's not a tree and if it has loops, then we can't make any guarantees. And it turns out this is one of the few situations where you can guarantee you'll get the optimum. And it's something to do with some of the combinatorial properties of k-matchings and 1-matchings. And so then we run this algorithm. It's guaranteed to give the optimal solution. It's one of those few proofs where loopy belief propagation works. And it works tremendously fast. You can download the code. Here's our runtime versus the Edmonds algorithm. And it's about, I think, 1,000 times faster on this particular size of the problem. But it's actually close to order n squared instead of n cubed. And there was a recent paper by Salas and Shaw that showed that message passing like this on matchings gets order n squared, which is a surprisingly fast result. So this is how the algorithm works. We send messages back and forth between the points and say who wants to connect to whom. It's like running an auction. And what's nice about this is even though it's a message passing distributed chaotic process, we're going to get to the optimum after running this auction. I think well, n squared times, or no, actually n times, bouncing back messages like this. And so in the end, this guy gets connected to 2 guys, this guy has only got connected to 2 guys, etc. But you can just do this by running an auction. It's related to some of these auction algorithms by Dmitry Vertsikis and other distributed ways of solving these auction problems. Okay, so now we can do k-matching. And here's an example where k-matching makes it, uh-oh, did I, my laptop still works, but, okay, yeah.
That's like a loose cable.
Yeah. Oh, is that?
This should be okay.
Okay.
That's good spot.
So here's why we actually got interested. This whole overpopularity crowding effect in high dimensions that we talked about, with everyone in the room picking central people too often, happens on real data. So here we're trying to visualize a bunch of websites. And we run k-nearest neighbors on how similar the websites are using the AOL data. And we were getting these types of visualizations. This is exactly the same problem of everybody picking really popular websites in the middle. If you just greedily grab your k-nearest neighbors, everyone connects to Google and Yahoo and all these other really popular sites. And out here we get complete disconnection. So if you run the k-matching, then you get this type of network. Instead of everybody just grabbing these really popular centrally located nodes, you get this nice network where now things like the airlines are out here on the top right. You've got Orbitz, American, and United Airlines, and so on, being laid out nicely together. So the k-matching fixes that overcrowding problem. And another thing we showed is if I want to use k-matching for classification, I can actually improve over k-nearest neighbors. So here's the idea. If I have a graph, and I've labeled some of the nodes now. This is a sparse graph. I've labeled these guys as positive and these guys as negative. What should be the label for these? This is a classification problem. So of course, everyone will say for 1, it should be whatever that color is, purple. And for 4, it should be labeled blue. So this is called graph transduction, or basically classification on a graph. And there are algorithms to do this. But if you build a graph using k-nearest neighbors, you get much higher error than if you built a graph using k-matchings. And it's again because of this overpopularity effect. So that those centrally located nodes everybody connects to, if they're wrong, then they just kill your performance completely. So a small mistake on that central node really is very damaging to your classification accuracy. So we've shown big improvements, and these are 3 different algorithms that do this type of classification, just using k-nearest neighbors in green versus using k-matching in blue. And so k-matching is making a huge difference for all 3 algorithms. Okay, so now I'll just talk very quickly about how we partition graphs. And you can imagine partitioning is a little harder than labeling because I won't tell you any of the labels, and I just want you to say which ones are the blues and which ones are the reds without giving any red examples and any blue examples. And so that's basically giving you a graph like this and say split it into 2 pieces, the blue piece and the red piece. And this is related to clustering. And clustering has been studied by the graph theory community for a long time, and they call it graph partition. Basically, I have a graph and I want to split the graph into two subsets, S and S bar. So the vertices S and the vertices S bar. And the cut criteria in at least theoretical computer science are this thing called the sparse cut, the edge expansion, the normalized cut. Basically, the numerator is how much cutting I have to do on the graph. That's the A value. The denominator is the size of the two pieces that I'm left with at the end, the size of S and the size of S bar. Because I don't want just one little node to be cut by itself. So the denominator encourages the two clusters to be big, not trivially small. So turns out the bad news for this problem is all these cut criteria are equivalent. So if I could solve one, I could solve the other. They're all NP hard, and they're all actually hard to approximate to constant factors. So there is no hope, basically. However, there is some good news, which is there are approximation guarantees which aren't constant factor approximations. So I can't give you this guarantee like I'm always going to be, let's say, 90% away from the optimal. The guarantees are going to get worse as the graphs get bigger. So I can do really badly for infinitely large graphs, but the hope is they don't get worse too fast. Okay, so the guarantee gets worse with larger n. We can't put a constant and say it's always going to be 95, 99%. It's going to be some number that grows with n, but hopefully not too quickly with n. So here, let's focus on the sparse cut. We want to find the cut that does the least amount of cutting in the graph and gives me back two big pieces, S and S bar. And so Ambul, Messolili, and Svensson in 2007 showed that it's NP hard to find a solution that's within a constant fraction of the minimum. So let's say the minimum is a cut of, let's say, of 80 or 0.8, sorry, 80%. You can't guarantee you're going to get something that's 80% times 1.1. That's impossible. A popular algorithm that people use in machine learning and in computer vision is spectral partition, and that just uses the eigenvectors of A. It needs cubic time. Actually, don't look at that value. You can actually do it faster than this. That's worked by Ng, Jordan, and Weiss, and Sheen Malik. It turns out that algorithm can't achieve this, of course, because that's NP hard. It achieves order square root of n times the optimal. So as n gets bigger, I'm doing square root of n worse than the optimal. And that's using classical results like the Cheeger inequality, for example. So let's try that SDP trick we did for embedding at the very beginning to fix these spectral problems. And it turns out there is an SDP that achieves not just root n, not just root n times the optimum. It achieves root of log n times the optimum. So that function grows even more slowly with n. And this is the SDP of Arora, Rao, and Vazirani in 2004. And they basically improved on the latent Rao 99 linear program. This was what motivated Akamai as a startup, because they said we can do this great sparse cut and edge expansion type of algorithm. Anyway, so this is a semi-definite program. What it's saying is, here's my graph A. Find an embedding of the graph. So I have a graph. Lay the graph out in some Euclidean space. So the opposite of what we did. We went from Euclidean space and built a graph. Now try to put the graph in Euclidean space so that if I and j are connected, the distances between them aren't too big. So if 2 points in the graph are connected, they can't go too far away. And then satisfy this set of triplet inequalities on the points. These are called L2-2 embedding inequalities. All this is saying is the triangle inequality should be preserved between the points, but actually not between their distances, between their squared distances. So this is strange because we're squaring the distances and saying the triangle inequality has to hold when I lay this graph out in Euclidean space. So L2-2 says no triplet of points can make an obtuse angle. So lay the points out. If things are connected, they have to be close. But never make a triplet when you're laying out the graph so that any triplet has an obtuse triangle in it. So this is fine. There's a theta of 20 here, a theta of 90. That's OK. But the minute this triangle gets obtuse, this angle is larger than 90 degrees, then we're breaking the requirements of this embedding algorithm. So that's what the algorithm does. And then at the end, once it's done this SDP, it runs this quick procedure to get S and S bar. And that's the final answer, and that achieves order root log n. And so here's our version of it, because this algorithm requires regular graphs. or K-matching graph. So all we do is we just start with the data, we compute the K-regular graph from it using K-matching, and then we run basically the Aurora-Round-Vazirani algorithm. And we have some extra extensions. I'm not going to spend too much time on them. We have some other tricks in there, but basically we're getting something like this root log n guarantee on the optimum. So the best way to cut the graph, we're getting root log n times that, just like the Aurora-Round-Vazirani. I won't spend too much time on the result, but we're able to apply this result to real problems. And we see, for example, on the clustering data sets, for example, clustering digit images, we do better than spectral clustering. This is the mutual information that it goes up. And as you vary the kernel, sigma, you also have a more stable performance for different types of kernels. If you use the wrong distance, you're still getting a better cut. Here's some other data sets where we clustered video sequences. Again, this is the algorithm. This is spectral and some other variants, getting just about 55 or 60% accuracy versus 90% accuracy when you use this matching and then the appropriate cut. So matching is very important because it lets you map to regular graphs and then run this technique. And another version of this we use to cluster some stuff for the NSA, and they give the best clustering out of several teams. Okay, so again, now we have some nice algorithms from the, we kind of took this from the computer science theory and graph theory community, but I think it's very valuable for machine learning and also for clustering problems. K-matching as well came from the graph theory community. So, and then these embedding results, some of it is machine learning, some of it's graph theory. But the key is you can do a lot of these machine learning and I think cognitive science problems by thinking about graphs and exploiting some of these really nice algorithms this community has built. So I'll talk very quickly about how to build these types of graphs on location data. So back to my applied side of my talk. So we have data at this company from about 4 million people who've opted in through using various applications and things like this, and we're collecting every few minutes to every couple of hours their location from their cell phones. So this is an amazing data set, I think, for social sciences and other applications. Here's, for example, a few users in Manhattan, and we have, I think we're showing a few days of each user and kind of the little trips they're doing around the city. So you quickly can start seeing the behavior and where people are going to back and forth from Brooklyn into Manhattan here, etc. We've got 4 million of these guys. I'm not going to go through all of them. And the first thing we did was just to visualize this data. And so we wrote this application you can download on your phone, on your BlackBerry or iPhone or one of these Nokia phones, which just shows you, and this is San Francisco, shows you where everybody is right now. And it also shows you where there are unusual levels of activity by running a simple Poisson model, saying this is above average. And so this lets you find where the crowd is right now. If you want to go to a restaurant that's lively, you can search for the busiest restaurants, busiest bars, etc. this way. Or least busy if you want somewhere quiet. And this is updated about every 10 minutes, just from all the data. But of course, the first thing everyone says is, well, this is great. These are all the people in the city, but I want to see people like me. So we want to do some analysis on all the users and figure out who's like whom and automatically cluster people and build this network. A little like Facebook, but the idea is not have people say, I'm friends with this person. If you co-locate with someone, we should be able to figure out that you're friends with them. Okay, so here we're showing it. So we haven't released this version. This is showing the users, but we've color-coded them with different colors, saying which cluster do they belong to. Okay, so this is their social cluster, let's say. And so this is a few thousand users in San Francisco. And what we want is a network like Facebook over these users, so we can say who's like whom and start clustering and saying, well, these people are very different than these people, and these are the blues, and these are the greens, and these are the yellows. And so the way we figure out who's like whom is we're basically going to look at how often two people co-locate. That's how we calculate similarity. Not quite a kernel, just how often do I co-locate with someone. But the problem is you can't really look at raw co-location because, for example, these two users, this guy works in San Francisco lives in San Francisco and works in Palo Alto. This guy works and lives in San Francisco. But it turns out they're both working at a tech startup. And so you can't just compare the raw latitudes and longitudes and say, oh, these people are coinciding, because they're coinciding semantically, not physically. So what we need to really understand is semantic coinciding, not physical coinciding, or co-location, I should say. And so we built a network of places to say, well, is this place similar to this place? And that's how we really bootstrapped the process. So we actually built a network of places before building the network of people. And the way we learned that network is we looked up some of the commercial activity at each street corner, some of the demographics at each, I think, zip code +4, and we looked at how people flow around the city to build a similarity of places. So this network now shows you, is place A like place B? Well, I'll draw a link between them and say they're similar because there's an edge between them, and how similar with some scalar value. So here's, we actually looked at the pairwise flow across the city and did something like PageRank. So a little like what Tom was describing, we looked at the transition across. Here we're just showing the top 200 bars and restaurants at night. And we looked at the transition matrix across all the different locations. So let me just rewind that. So, and the idea is to look at this transition matrix and try to find a lower dimensional version of this transition matrix or graph. And what that does is it captures the similarity between places, because let's say we look at one bar on this side of the city and one bar on this side of the city. If the inflow into this bar and the outflow into this bar are identical to the inflow and the outflow to this bar, then they're actually getting the same types of people and the same type of crowd. So if we believe that hypothesis, that similar inflow and similar outflow means similar places, then we can compute a similarity between places and then run this kind of dimensionality reduction algorithm, which moves the bars and restaurants so that places with similar inflow and outflow get brought closer together. So that's what is happening here. We just run this MVE algorithm, and it brings places with similar inflow and outflow close to each other. And here we run a clustering on this to label the types of bars and restaurants as pink or purple or whatever it is. Yeah?
So how do you deal with time? People being at different places at different times?
So we actually solve this problem on different 4-hour chunks of the week. And we look at the actual Markov transition matrix, not just statically, but also transitioning to different chunks of time. So that's the most recent version, but I don't have a nice animation for that one. Yeah?
What values of K does this start to become slower versus being a very quick operation for a K matching?
So we run K matching on the Netflix data. It takes under 10 minutes. So we can run it on 1 million nodes on a laptop in about 5 minutes. It doesn't really doesn't affect the runtime of the max product algorithm, because you don't have to store data structures that grow with K. So well, let me double check with Bert about that, but it doesn't affect the runtime too much. The real quantity that grows is n. So that's where the runtime really slows things down. We've run it on, well, not quite K, close to n, but.
Right, because I figure you could get that star shape, right, in that kind of situation.
Mm-hmm.
Since the central node can now have some high number of links.
Yeah.
There may be a ratio of K to n.
Yeah, so you might want to use K to be logarithmically related to n somehow.
Or something, yeah, it's pretty small.
Yeah. True, yeah. So, but we have run these algorithms on really large amounts of data. Here's another thing we're looking at, which is just what commercial activity is at each place. You can download that from the standard industrial categorization database. The government keeps a database of every business in the country and what code it fits in. Is it an Italian restaurant? Is it a high-end retailer? Is it a bank, etc.? And you can also look at all the demographics, again, from the government data. So we can get a very good description of all the places and form these clusters of places. And then the way we describe each user is by this probability matrix of, for each week hour, what's the probability they're in Italian restaurants? What's the probability they're at a bank? What's the probability they're in a blue bar or a red bar or a high-end neighborhood or a low-end neighborhood for every week hour? So we convert this spaghetti of GPS data into a probability model. And these are 9 users with their probability models for every week hour. And then we can just calculate how much these users co-locate, not physically, but semantically, because these matrices have abstracted away location into something that's meaningful. So coffee shop versus this latitude and this longitude. So you can calculate co-location, get a pairwise score for all people, and then we run K-matching, and then here's a layout of a piece of the network with a few thousand users, not all, not the 4 million users, but a few of them. And so now this is our Facebook network built from just people co-locating, not people saying, I'm friends with this person and they accept. But actually the K-matching does require the person to accept in a way, because if you're close to someone and they're not close to you, then you won't get linked. So it's doing a little bit of that Facebook reciprocity, but kind of at a loose level. And now this network is what we're using to do interesting things like churn, which is someone going to leave the carrier because they're fed up with Verizon and they want to go to Sprint? Or what ads will one of these users respond to? If I know the network and this person clicked on an ad and liked it, these people might be more likely to click on it than these people. And so we tried that by running the labeling algorithm we talked about for ad clicking. And this is the baseline, which is when you don't use location information, you just look at what I clicked on before to predict what I'm going to click on next. That's the Amazon model. What books did I buy before will predict what books I'm going to buy next. If you combine that with also somebody's location network, you get an improvement of 1.8 times in the accuracy predicting the ads that they'll click on. And then we've also done clusters on this network and found some interesting clusters. Basically, there's the young and edgy people that seem to go out a lot. There's the mature people that don't go out, spend nights at home. There's the weekenders and so on. So you can, again, do clustering on this network. We're still working on this part. It's and I'll just wrap up here and say, again, there's a lot of really nice machinery from the graph theory community, and machine learning, I think, has started using that. Social networks and social scientists have also started using some of this graph machinery, and you can also work with networks of real data, not just these online networks that we can download from the internet and so on. I'll stop there. Thank you. Yeah.
What's the reason for squaring the distance?
The reason for squaring those distances and those triangle inequalities?
Yeah.
It's to prevent any of the, well, all the triangles have to remain acute. You can never get an obtuse triangle. But that tends to put points on the corners of a hypercube.
Yeah.
And if the points are on the corners of a hypercube exactly, then a random cut will split the graph into two nice pieces. So you're trying to get something that looks like its corners on a hypercube and get this nice clustering property. The triangle inequality, the L22 triangle inequalities encourage that.
Yeah, we want to keep the triangle inequality, but maybe there is another function of the square that's to provide each other.
So you want a higher power than the square.
Yeah, you may want to optimize the function.
So there's a sequence of these types of higher order constraints, and those just grow the semi-definite program very quickly. So now the semi-definite program involves looking at all triples. So you can get more complicated by looking at higher order versions. Yeah, so that's the simplest one that still has an efficient solver, for example, and it gives you the square root log n guarantee. And there is also a theorem that says you can't do much better than square root log n. There's a theorem that says you can't do better than square root log n, for example. So you're already close to that, but that's kind of a lower bound on how close you can approximate sparsest cut before p equals np. So something like this. It's not my work. This is the graph theory and theoretical computer science community. Yeah.
So when you're comparing similar places, you said that you have 4-hour chunks of data. So do you say A and B are similar at this chunk of the day, or you compare the profiles for A and B to determine they're similar?
So right now we've actually started looking at transitions on this network, which doesn't have nodes for each place, but also has each place for every different 4-hour chunk, there's a copy of that node. And then you look at transitions in kind of the week hour chunks as well as between places. And then you do this Markov transition matrix on that bigger network, which grows the network by about 40-fold.
How big is N, or how many days do you need to estimate your model?
Well, for some of these users, it quickly converges after 2-3 weeks. You don't see too much movement in these matrices. They kind of settle down. But if somebody changes their behavior, you'll start seeing the probabilities change. So right now, we haven't really worried about that too much. But yeah, maybe we should be worrying about people changing and saying, okay, well, I was unemployed and then suddenly had a job, and so the matrix will change and you start going to work between 9 to 5 versus being at home between 9 to 5. Definitely, yeah. Mm-hmm.
How do you quantify performance of your models? Is it like, can I predict where a particular person will be at this time? If you have different models to compare, how do you do that?
So here we just computed test likelihoods on, so we train the model on a month and we compute the test likelihood on the next month. But for a real quantitative performance measure, we also did this clicking prediction. So one of the clients has what people are clicking on in addition to their location data, and they want to predict the click behavior as a response in ads. So then we can show that the location profile helps you improve that clicking. So that's another quantitative measure.
But predicting location itself could be a goal. Right?
That could be another goal, yeah.
Especially for intelligence.
True.
agencies.
We haven't really done this kind of predicts where someone's going to go to next. And in fact, a lot of these models, we started off with Markov models instead of these weak hour models, which are better geared to predicting where you're going to go next. But we didn't get as good likelihoods because people really follow a weekly schedule. So it doesn't really matter so much that I was, at lunch and what's my next possible move afterwards. What really matters is I have to be back at work at 1:30. So if I go to the restaurant, it doesn't matter what happens, or if I didn't go to eat lunch, I still have to go back to work, for example. So these weak hour models were a little bit better than Markov models. Even though we wanted Markov models to win, they actually didn't work as well.
There's on social dynamics kind of semantic tools, there's this problem that, and I think that there's a richer gets richer kind of effect. So you're saying that people wants to meet similar people to them, but you would have like something like people listen to Britney Spears, and so you would suggest Britney Spears to everybody, but actually nobody likes Britney. That's extreme.
Yeah.
That's extreme, but it captures the point that I think somebody is starting to suggest alternatives to this concept.
Yeah.
Because it's frustrating in some point of view. Some point of view is nice, and sometimes somebody probably has a schedule and meets all these people, but he doesn't really want to be there.
Yeah.
He wants to meet different.
So it's true that this rich get richer model isn't the be-all end-all for all these social networks. So some people have shown that on some networks, but there's a paper by Pennock that shows, for example, that in many settings you see people kind of go to a certain limit of the number of connections they're going to make on these social networks. It doesn't keep growing because there are some resource constraints. And so I think there's two reasons why you see some of these power laws which you're referring to. One of them is artificial, just because high-dimensional data tends to create a power law. Another one is because there's a real power law because there's no resource constraint. You can connect to anybody on Facebook and you get these really strange mega users. But we like the idea of a little bit of a resource constraint. You can't be at all places at any one time if you're physically running around. That's not completely true because, again, when we tried this, let me just maybe jump to a slide that shows you what I mean. If we run k-nearest neighbors to build these networks, again, we got this type of star diagram where some of the users, which are, I don't know what these guys are, maybe mailmen or couriers, they are always running around everywhere and they get picked by everybody as their nearest neighbors. So I think that's, you either want to break that or you want to exploit it. But I actually think, I like the idea of having a k-matching instead to avoid this overpopulated kind of linking phenomenon.